evening, everybody. Welcome to another one of our Leica Academy evening video webinars, live from Brisbane. And a lot of you I know are in Sydney and Melbourne, but I'm in Brisbane, and we also have Peter Karbe, of course, in Germany here. So I'll welcome him in a second. Oh, here he is anyway. So tonight we have a very special occasion, really, because we're going to be hearing from the maestro himself, if I can call him that. Peter Karbe is the man behind these M lenses and lots of other things as well, which he'll be telling us about over the course of 2 webinars. And I think those of you who are already shooting on Leica cameras will know there's a certain je ne sais quoi about Leica glass, which is, it's not a myth. It's absolutely there. It's subtle, but it's absolutely there. And it's people like Peter who are responsible for the voodoo and the secret sauce that goes into lens design, which from what I gather is a highly mathematical, very complicated process, of which I know virtually nothing. So I'm looking forward to learning a bit this evening as well. So we're very lucky to have Peter talking to us directly. This is just for Leica Academy Australia. And he has a presentation that he will go through, which takes about an hour. But he's asked me to say that it's perfectly okay to ask questions. And what I'm going to do, as I normally do, for those of you who've been to these things before, is you can use the chat or the Q&A. I know I always say use the Q&A, but people use the chat anyway. I'll see both of them. And I will do one of 2 things. I will either save questions for the end, which might require a bit of deeper explanation. And I've already got one, actually, which will require a bit of more explanation. Or if a question is sort of needs to be answered now, I will butt in and ask Peter to answer the question. So anyway, without further ado, welcome, Peter. Do you want to unmute yourself and say hello?
Thank you very much for the introduction. Thank you very much for giving me the chance to have to show this presentation. Yes, my name is Peter Karbe. I'm in charge of optics at Leica, and I've been working for Leica more than 30 years now. And I started as optical designer at Leica. Before that, I had an apprenticeship as photographer, joined University for Photography in Cologne, and then I joined Leica 1986 to be precise. So, and now I'm the head of the Optical Development Department within the R&D business. Yes. Now I would like to talk about the presentation. Do I need to share again?
Yes, you'll need to start your share screen again. So I will let you take over, Peter. So away you go, and I'll monitor the questions. And as we said before, if there's a question that comes up that needs answering, I'll turn my video back on, and we can answer the question. Okay. So away you go.
So can you see this?
Not quite. Yes, there we go. All done.
So today we are talking about M lenses and about the history of optical development at Leica camera. So before we start with the M lenses and all these things, we need to know how photography was before 1900, and it was exhausting, time-consuming, and complicated, and know how it was required very much. Yes, and one reason for that was that large format cameras normally were used. And large format cameras, you need to stop down very much to get a certain depth of focus. And that required exposure time, very long exposure time. Perhaps somebody of you will remember 21, 22, 23, 3 seconds exposure time. And this was the reason for very stiff photography at that time. Yes, especially for portrait also. And Oscar Barnack, he had an idea for the 35mm camera at Leica, and his idea was to create a system with which you are able to take snapshots, or we call it in Germany Momentaufnahme. And he had the idea to take a smaller format to get a better depth of focus, even though you do not stop down so much. Yes. And so the reason for that was that if a large format camera, like here, you have a large focal length, and a large focal length is, the depth of focus is very small, and you have to stop down very much. And so due to the low sensitivity of the film or the photographic material at that time, you had to exposure longer time. And so with a smaller format like 35 millimeter exposed here, you, have a shorter focal length. And with a shorter focal length, you have a larger depth of focus with the same F number, yes? So let's go through again here. This was explained already. The aperture is small to have the depth of focus. And with the Leica format, with 35 millimeter format, you can wide open the aperture and this exposure time is shorter. And with this exposure time, you can realize the Momentaufnahme, the snapshot. And this is one of the examples of the proof of concept from Barnack himself. He took a picture of Wetzlar during the flood in Wetzlar around 1914 or 1915. Yes. So, and the first Leica handbook written from Fritz Fied, 1930, there is written that the biggest advantage of this system is the larger depth of focus in with wide open aperture. Yes. And Oscar Barnack, you know the story. He developed the Leica, the first 35 millimeter camera. But it was not only the Leica. There was Max Berek, an optical designer, at the same time at Leitz. He was involved in microscopy and polarization microscopy and all these things. But by the way, he did some optical design studies and he designed the first lens for Oscar Barnack. And this combination was a starting point for a good and proved good optical concept, yes. So, and they both together, they developed the Leica, not only Barnack, but also Max Berek. And when you look into the brochures in the older literature, you will find some interviews with Barnack and Berek, and they explain how they developed the design or how they defined the design targets for this system. And this is very important for me still today, because it's a concept we still follow, like they did. So the 35 millimeter format, 24 by 36, and the camera, the lens and the camera together, this makes a Leica. And they said the design targets were done or were defined in a very simple way. They took a postcard, a black and white postcard, where you can see a black and white picture, and they counted the dots. How many dots do we need to get a perfect postcard image? And they came to the conclusion that 1 million dots are necessary to get a good print on a postcard, or a good picture on a postcard. And with this, they defined the circle of confusion, the allowable circle of confusion, or the minimum size the aberration should be. And this, they defined 30 microns. And when you recalculate this, you come to an equation where 900 square millimeter film area is needed, and here you see 864. So this is a very rough assumption they took. Why do I show this? So pixel counting is not new, because they counted the pixels or the dots at that time. So still today, we need to count pixels. The second is that this depth of focus tables you see today are still based on the circle of confusion 30 micron. As you know, perhaps the resolution of the film is, or of the sensor, I need to say, of the sensor is much better than 30 microns. Today we have 6 micron, we have 4.2 micron pixel size. And internally, we define depth of focus in a different way, not with 30 microns, more that tendency we like to follow, that 2 pixels define the circle of confusion. Yes. So this is the first optical design data of the LMAX done by Max Berek in 1921 is the date of this. So 22 is the latest change in this design. Yeah. And I need to highlight that optical design at that time, it was not so easy than today. Today we have computers, we have software, we have a lot of things. At that time, they had different tools they need to use, and logarithm tables here. And this logarithm table is quite interesting because Karl Metz did this logarithm table, and Karl Metz was the first optical designer at Leitz, and he did his own logarithm table because he didn't trust the other ones. He wanted to have a very precise logarithm table, and they used these tools here to and all writing by hand, and this took a very long time. And I also want to highlight that Max Berek, at that time in 1930, he published a book, Basic of Applied Optics. The first edition was done in 1930, as I explained already, and in his foreword he said, you want to convey an understanding of the nature of technical feasible image systems based on practical problems. And this is a very important sentence for me, I think. Yes. And the second edition was done, I think, 1970. This nearly unchanged second edition existed till 1990 or so. And this publication is the basis for many patents you find today. So the Leica was done 1914, 1913. But it took a long time before we had the first Leica. After World War I, they decided to build the Leica, and the official introduction was done 1925. Yes. And the rangefinder was added. It was not implemented. And this is one of the first advertisements. It was not named Leica, it was named Banach camera. The Leitz Banach camera was the first name, yes. And later they changed it to Leica, Leitz camera, Leica, yes. And
Peter, can I just butt in for a second? I've got a question from one of our guests. So Mark Chan would like to know, and this is probably appropriate for what you've just been talking about. Hello, Mr. Karbe. How would you optically characterize the Leica Look describing Leica lenses? Or are you going to mention that later in the talk? Because there is a distinct look, and I was wondering how you would describe it yourself.
Let's go through the presentation, and later we can discuss if it's not clear with my presentation.
Okay, let's do that. All right, then. Thank you.
It's not only design; it's also production and test and acceptance conditions we define and all these things.
Okay, all right, we'll do that.
Thank you. So, and the main advantages of this system: it's a fast system, it's very fast lens, it's very sharp, and all these things. Unfortunately, I only have a German advertisement. This is a copy I have in my bibliothèque. Yes. So 1930, the first Leica was done. It's mirrorless, easy to use, and compact, and with interchangeable lenses. When I talk about easy to use and compact and all these things, this is from the perspective at that time. I also will do a retrospective judgment later. Yes. And this was the first CSC. Today, every mirrorless camera is named CSC, compact system camera, yes. And this was one of the first CSC in 35 millimeter format. Yes. So, and 1932, the Leica 2 was introduced with integrated rangefinder and screw mount, and this was a system. And here's a second advertisement, and here this is in English. With automatic focusing has a totally different meaning than today we know about that, yes, and for all Leica lenses, yes. It's very funny. Yeah. So, and then after that, 1950, the Leica 3F appeared and were introduced, and Yes. I want to talk about lenses mainly. Just that's at the beginning I talk about the camera. And Fritz Fied, I already talked about him. He had the second edition or new edition 1940. This is 15 years after introduction of the 35 millimeter format. And he has he did some retrospective aspects about what at the beginning of the 35 millimeter format area, how the customers and the dealers judged this system as an annoying innovation, and large formats users fought back. Yes, Leica focal length is too short, and who needs 36 pictures and all these things. Very funny. And why do I highlight this? Today we have the same discussion between 35 millimeter format and mobile phone optics. Yes, it's the same discussion. Yeah. Before I continue in presenting lenses, I would like to introduce a perceived performance as a proposal. Perceived performance for you as a customer. And I would like to talk about 5 points as light flux, compactness, image performance, ease of use, and robustness. And I explain each parameter. So light flux, and sorry to say, but it's a little dry what I'm explaining now, but otherwise I can't explain technique. So light flux is a whole light you transport by optics. The F number describes only the illumination per image point, and light flux describes the whole light which is transported through the optics. And this is very important for optical design, and also very important for the camera use or for the lens use, because light flux is equivalent to the equivalent F number. So which depth of focus can I expect with which light flux in principle? Yes. And here's the equation for that, but you do not need to know that. Important is the sensor area is important, and the F number here by square. So if you compare different systems with different sensor sizes, you need to know that the light flux is reduced by the sensor area when the sensor area is smaller, or vice versa if the sensor area is bigger. Reference today for every discussion is in terms of equivalent F number is always a 35 millimeter format, so the Leica format. Yeah. So compactness, the compactness is described from my point of view, the first surface of the lens to the image describes the overall length of the system. But for me, if you compare different sensor formats, you need to know the relative size, and the relative size is defined by overall size divided by the diagonal of the sensor. For today's discussion, we do not need to talk about this system, because we are within our format, within our 35 millimeter, we are talking about M. But if we compare with APS or so, we need to talk about the overall length divided by diagonal and by relative size. So image performance is defined, for example, by MTF values, as higher as better, by the best F number. Best F number means very often we are asked which F number is the best to get best performance. This is based on the knowledge from the past. So if you, and I will talk about that later a little bit more in detail. And ghost and flare reduction is also a point where we have to look at if we talk about image performance. And now I would like to make a sidestep to the MTF modulation transfer function. I would like to explain it in some slides here. MTF describes resolution, frequency, and contrast modulation for the image. And if we have here, if this is 1 millimeter width or negative or a sensor, doesn't matter. And this is a frequency, one line pairs per millimeter. So one black line and white line. And here 5 line pairs per millimeter, 10 line pairs, and so forth. And we don't talk about sharp edges, we talk about sine or cosine function. So in the middle here is black, and then it goes down to white in a very smooth, how can I say? It's not a sharp edge, let's say in this way. Yeah, okay. And if we talk about modulation, 100% means that white is white 100% and black is black 100%. And 80%, if we look here for this 10 line pairs, modulation 100% looks like this, 60% looks like that, 20% you can see it still the structure of the modulation, but the contrast is very low, and 0% you see nothing at all. And the contrast is defined by bright area minus dark area divided by bright and dark area. So for example, if you have for white you have 225, and dark is not really dark, it's there 25 as a value, so you have 80% contrast. So how does it look like in frequency? If we talk about frequency, what does it mean? So here I took a picture of an old house in Wetzlar, and these are the low frequencies. Yes, here this big bars here. And these are medium frequencies, and these are the high frequencies and the very high frequencies. So if you look within this window, the high frequencies you can recognize. So, and if we talk about MTF curves, like here, this is the MTF contrast indicated. And here are 40 line pairs, 20 line pairs, 10 and 5 line pairs. And this is the image height. And image height means from here, from 0 to 21 in the edge. Yes. And so this is like that. And due to the fact that we are rotational symmetric systems, we should have rotational symmetric systems, we can say, okay, image height 12 belongs to this circle here. Yes. And image height 15 belongs to this circle, is cutted by the sensor and so forth. And 21 is the edge you can find only here in these areas.
Hi, Peter. Just
yes,
going to interrupt once more. This is a question that I don't actually understand, so I'm going to pass it on to you. How is what you are discussing with MTF linked to Fourier transforms?
Fourier transformation. So we measure a slit, yes, and it's directly connected to that. So in principle, the Fourier transformation of the pupil delivers the image performance, and so it's a mathematical question, yes. But it's directly, we measure a slit and or an edge, and out of the edge with a Fourier transformation we can get the MTF curve. Yes.
Okay, I hope that answers your question, Valeria. Tricky one.
So here we have a good lens with 40 line pairs better than 50%. Yes, and here is the original, and this is the MTF delivered by the lens. I hope you can see a difference. I don't think so. And this is a bad version here. Yes, a bad lens where image height 12 has a bad performance for the high frequencies, and here you see the result. Yes, nearly no resolution at that time. 20% are low, but the 20 line pairs are low, but still visible. Yes, and 5 line pairs. So 5 line pairs give you a rough idea how the first impression of the image will be. Is it foggy or is it clear? That's one thing. So, and here I have an animated slide with bad MTF and good MTF, and then you see perhaps the differences. In principle, the sharpness suffers when you have this performance. Yes, it's not sharp. And if we talk about line pairs, so this is an image taken by 50mm focal length, and here the rough structures have one line pairs on image. One line pair is 4mm, and these are 5 line pairs on the image. And these hairs here are 1 line pairs on the object to 4.2 millimeters, and due to the magnification or the, yes, we have 100 line pairs on the film or on the sensor. So image performance is clear. Now we talk about ease of use. Definition of ease of use is convenience for the user, assistance by the camera, automatic functions, and how much knowledge is needed by using the system. So robustness is durability tests. We do a lot, and this is one of our core values we try to keep. This is durability, humidity and moisture resistance, shock proof, and all these things. Yeah, scratch proof. This is a very, very important thing, especially for M lenses. Yes. So, and when we give for each parameter a point from between 1 and 10, we can judge about the optical systems. I will do so for the next part of the presentation. So, and here is the lens number 1. Yes, it's very poor and doesn't exist because each lens element has more than this. And lens number 2 seems to be perfect. And we call it in German eierlegende Wollmilchsau, or in English, I know, flying submarine tank. Everybody would like to have that. And it's not easy to realize this. So, and by all discussions we will do now, I would like to ask you to stay in the tradition of Paul Wolf. Paul Wolf published a book, a very important. Paul Wolf was one of the pioneers of Leica photography or 35mm photography, and he published a lot of books. And this is, for me, one of the most important because he discussed with professional photographers and normal users what is better, big, large format or 35mm format. In 1940, he published this, and this is interesting because 15 years after introducing the 35mm format, this discussion still existed. And what did he do? He published images he did with 35mm and with large format, and he mixed it. And he said, I don't tell you which one is taken with which system. Please decide by yourself which one is done. And then he discussed with professionals that the Leica photography has its own area where you can use it, where you can compete with or can do some things better than with large format, and so forth. And still the discussion today we have, which is the best format. And it always depends on what do you want to do, how much effort do you want to put into your image taking processes and all these things. Yes. And so I like this book very much. Unfortunately, it's only in German. So let's go to the first CSC, Leica 1, mirrorless, interchangeable, easy to use. Today it wouldn't be easy to use because no automatic functions, but at that time it was easy to use. And here are the first generation of screw mount lenses from Leica. These are the 28 5.6, for example, the 50 3.5, and all these things. And this is the lens shape, how the setup was done with how many lens elements and cemented or not. And when you look at that, you can see a certain footprint of that. And the footprint is that there is always 3 groups. We have always 3 groups of lens elements. And the reason for this is that at that time, Max Berek and his team didn't have coating, anti-reflection coating, and to improve performance, you need a certain amount of elements. But at that time, you couldn't increase the amount of elements in terms of groups. Only 3 groups were allowable. If you implement more, you introduce so many ghost and flare that the improvement by adding a lens element was destroyed by ghost and flare on the other side. And that's the reason why always 3 groups of elements were done in this. And when we now look at the perceived performance, I did the judgment, you can do it by yourself, but this is my judgment. The light flux was not that good, 6, because the F number was 3.5 or 2.8, and so the compactness was quite good, yes, still compact, can compete with today's lenses. The image performance 6, why do I say 6? Is in the brochure you could read at that time, please stop down 3 steps to get best performance. Yes. So this means you can use it wide open, but mostly to get shorter exposure time. If you want to have better performance, you need to stop down. Ease of use from today's perspective was not that good, because from today's perspective, yes. And robustness is 8, because today you can use these lenses still, yes. So, and now I would like to introduce a graph I will show later again. Here is perceived performance, and here is the size of the lens. And there is a simple routine. If you want to improve the performance of a lens, you can enlarge the system, and then you can improve the performance. But without enlarging the lens, you can't. It's very hard to improve the performance, and here are the limits. And this was state of the art at that time, and here was a limit. And in principle, here was a limit at that time due to the number of lens elements you can use. Yes. And this green field here, I call it green field, is the area where innovation need to happen or need to be introduced. We want to get better performance, perceived performance, without increasing the size. This is a simple view on the things, yes, but it explains a lot, I think so. So in innovations, this is the hint to 1954. I call it the year of innovations, because the M-System was introduced at that time. The viewfinder with integrated rangefinder, the M bayonet was introduced. I think you know it already. So the M-System exists now for more than 60 years. Yes, it's quite good. And here's a rangefinder. You know it already. The functionality and the M bayonet. This is the official or the obvious innovation. Everybody can think about that. But internally at Leica, there happened many more innovations. The one was glass technology at Leitz. Leitz developed his own glass materials to get better performance, and coating technology they developed. And I would like to explain it a little more in detail. Leitz had installed an own laboratory to create new glass materials, and I say we had the chance to create here low dispersion glasses here, yes, and high refractive glasses here, and here glasses to improve the performance in terms of color correction on the flint side with larger dispersion, but very necessary to correct best color performance or apochromatic correction. And coating was done to reduce the reflection. Normally you have on each surface 4% reflection or more. From the lights come in, 4% is reflected, and this introduces ghost and flare. And with a single coating, anti-reflection coating, you could go down to 2% or lower. Today we have much lower ghost and flare, much lower reflection with our multi-coating systems. To be honest, Lights didn't invent the coatings. This was done by Mr. Smakula, and he was an employee of Lights, of Zeiss, sorry. And he invented the patent file was filed 1936. And during World War II, the regime took over the patents only for military purposes, and after World War II, everybody could use these patents. And we used we needed a longer time to introduce it, to implement it in our optical design systems or in our optical systems, because the first coatings were not so good to handle. If you clean the surface, suddenly the coating disappeared, and so this was not so easy to implement it in production for photographic purposes. So, and with this innovation, the second generation of M-mount lenses were prepared, and so we get the newer version, the M-mount lenses, mostly designed by Mantler and his team in Canada. A lot of systems. And if you look at the second generation and to this drawing about the innovation, so glass technology enabled us to improve the performance without increasing the size or reduce the size by keeping the performance. And with coatings, we could increase the lens systems in terms of more lens elements and make it bigger, yes. And so here, I think it's clear innovation are needed to improve systems. Improvement, there always was a fight at Leica and with other competitors who has the fastest lens and so on. And at Lights, we started in 1966 or before that to try Asphere technology to implement. And this was the first one, the Noctilux-M by 1.2, 50 millimeter, and two Aspheres on the first surface and the rear surface. But to be honest, the production and the verification of these lens elements was very complicated, and in principle, it was an economic disaster we had to face. Lights spend more money to build the lenses than they get from the customer at the end. Yeah. And then after that, the successor was Noctilux 1x1. We introduced, and this was done by Mantler in Canada, and he implemented glass technology, high refractive index glasses here. We call it Noctilux glass with refractive index 1.9, for example, yes. And here's the performance. And here you see that stopping down was necessary to get best performance. The MTF is very low here, is low and very low here in off-axis. And if you stop down, you get better performance. And this leads to the perceived performance for the second generation. The light flux was much better. We have one Noctilux, the first Noctilux. The compactness is still there, yes. The image performance was improved, but in the brochure you could read, please stop down 2 steps to get best performance. Available light lenses, we call the Noctilux or so. This means you can use this for available light situation where you need short exposure time, but if you need to get best performance, please stop down. Robustness is also still there, and ease of use, of course, better because the camera became rangefinder camera. Yes. So the M-System as a traditional CSC was born in 1954. So sounds strange, yes, traditional CSC. And the limitations of the analog system was no zoom lenses, focal length range is limited, the focus focus distance, close focus distance 0.7 meters, and no ease of use at the time. From today's perspective. And the advantage of the M-System, compact, discrete, fast lenses, high performance, bright viewfinder, and robust, yes. And the M camera had the first challenge in the 70s, or we can say the first crisis with the M camera was the introduction of the SLR cameras. The advantage of the SLR cameras, what you see is what you get. Wider range of focal lengths were available, zoom lenses were possible, and close focus and macro was able. But at lights, they knew there are some certain advantages of the system. You see more than you get. When you look through the rangefinder and you have a 35 or 50 millimeter, you see the frames and you see what right on the left side of the scenery you take with the lens. And then you can decide when do I need to push the button, for example. The brightness of the viewfinder is always the same. It doesn't depend on the F number, and the performance is in a compact size. Yes, please. Question?
Peter, so got a question for you. Actually, same question from two people, so I thought it was important. They would like to know if you are using one of the current high quality lenses, does fitting a UV filter on the front of the lens change the performance of the lens at all? Or any comments you have about putting filters on the front of the current Leica lenses?
So a filter is an optical element and it need to be a good performing lens element, yes. So a flat surfaces should be, and the mounting should be perfect. So reducing the light that is going through, so for example, UV improves a little bit the performance, yes. And I understand everybody who buys a lens from Leica wants to fit it with a filter to protect. I understand fully. So, but it need to be a good filter, yes. Otherwise,
okay.
It can introduce astigmatism and coma and reflections, so ghost and flare, if it's not a good filter.
Get a good one. Okay.
Yes.
All right.
So,
thank you.
At that time, the management in Wetzlar planned to stop M camera production. This was really a big crisis. Fortunately, the colleagues in Canada, they decided to take over the M production because they needed the M camera to continue the production of M lenses. Most M lenses were done in Canada at that time. It's located in Ontario, Midland, Ontario. Yes, still there's a factory. Yes. So, and they took over, and so the M camera survived. To make it complete, 1984, Wetzlar, the camera moved back to Wetzlar, and development and manufacture was done by the colleagues in Wetzlar. So let's come back to the history of Asphere technology. So I explained already that the first Asphere lens, the Noctilux, 50 millimeter, was a catastrophe because the production was very complicated and the outcome was not, the yield was very bad. The second version, but we didn't stop to develop new technology regarding Asphere lenses. And so the new machines and new measurement systems were implemented, but it was still a catastrophe. This is a Sumilux 35 spherical. Again, Lights invested more money than we get from the customer at the time, yes. But we didn't stop. And then we did a cooperation with Hoya and with external partners and shot, and now we have a pressed Asphere technology we implemented with the Noctilux-M 35 ASPH, and this was the first Asphere lens where we successfully implemented technology and economical success we could see. But we didn't stop, because press technology has had some limitations regarding size and regarding shape, regarding lens glass materials, and so in parallel we developed a new Asphere technology production line where we polish Aspheres. With polishing, is more expensive than pressing for a big quantity, but we are more flexible and regarding the shape and regarding the materials. And so we implemented all these things. And the first lens I would like to highlight within the M-System is a 90mm aposomicron. And this was, aposomicron means that the apochromatic correction was done. So the color correction was done very well. And for this, we needed the special glass materials I explained already. We did at lights in the laboratory. So, and here you see high performance, wide open. Stopping down improves a little bit, but there is no need to stop down to get best performance. You could use it wide open, and this is most important. The processes for the Asphere technology, all these steps are shown here. The grinding, 2D measurement, correction, polishing, and 3D measurement by interferometer, and implementing a new fine polishing machine done in Rochester. I think this is done. The technology was developed in Rochester, and again 3D measurement. All these steps an aspheric polishing lens has to follow. In comparison to the workflow for spheres, is only this grinding and polishing, and of course measuring, but these two steps are only necessary for spherical lens elements. And as we were pioneers in implementing Aspheres within high performance lenses, and we did a lot, we learned a lot, and we fail a lot. We failed a lot, and we do the fine polishing technology not to get best performance in terms of MTF, but to get best performance in terms of bokeh. Because if you use the normal polishing technology, you have some irregularities on the Asphere shown here as rings. We call it onion rings. And you will see it in the bokeh, in the defocus of highlights. You can see this. And to get rid of that, we use this technology, the QED technology, I explained already, the fine polishing technology. And this is very expensive, of course, but to get best performance, not only in MTF terms, but also bokeh. And this is the part of the Leica Look, yes. The next part of Leica Look is not only design. Of course, we have a certain concept in designing the lenses, but also we have to have a look at the production. And the best lens it's not possible to perform if the housing and the assembly does not fit to that. Housing means the lens barrel, and the fixtures and all these things we need to implement within one lens. And for example, if you have this housing and the lens is decentered within this housing, it will stay a bad lens. And due to get best performance, we developed a lot to get a higher precision. And so, for example, we put the lens within the barrel, and then we machine this part afterwards, yes. After assembly, we do a final machining or a final adjustment within the mechanical parts. And so we get highest performance and good tolerances for the lens element within the housing. And then we can align, yes. And this is also one part of our concept to get the Leica Look. Yes, test and acceptance conditions. What is allowed and what is not allowed, and how can we realize these tolerances? And for this precision machining, we develop with partners special setups, machines. Not everything is done in-house. We also have external partners who helped us to realize this. Microscopy, like a microscopy, is doing the same, but with one step further in terms of precision, but much smaller sizes. So 10 times more precision, but 10 times smaller lens elements. In combinations, they do such things. So, and so some parts of our Leica Look are based on that what we know about microscopy. In the past, we knew about Leica microscopy. So let's continue with the Noctilux 1 by 0.95. This is the latest Noctilux 50 millimeter we have. And there we implemented everything I explained already. So Asphere technology, glass technology, floating elements to improve the performance, not only at infinity, but also in close focus. And all this mechanical issues here. This is the older version of the Noctilux, and this is the latest version. Much more mechanics we had to implement because due to the fact that focusing controls not only the connection between lens adjustment and rangefinder, but also it's had to control the floating element movement. So we have 3 lens barrels, focusing mounts connected together, and this needs a very, very high precision. Not only machining, but also our employees in the optical shop or in the mechanical shop, they need to grind this focusing mount manually. The final precision is done there. So that's it's always soft, but no backlash. Soft but no backlash, and this is very, very complicated and depends on the craftsmanship of our employees in the mechanical shop. Yes. So, and all these things we do, we include it into the Noctilux system. Yes. So, in the 3rd generation of M lenses with Asphere Technology 3, I name it 3 because it's press technology we use today. As long as the lens element is small enough, we can press. As long as the lens element has a certain shape, we can press. We use press technology. And if we need more, we do our Asphere Technology 4 grinding and polishing Aspheres we do in-house. And this is another presentation, Noctilux technology driver and light giants. The Noctilux always was a light giant, was a technology driver. These systems forced us to do the next step. How can we improve? Which step do we need, and so forth. And why are we doing this? For what? Taking picture like this, and this is always the reason why. This is the reason why I always say, please never stop down. Never stop down if you do not need the depth of focus. Use the lens wide open. The latest lenses are always designed to be used wide open. The money you pay for this is mainly to perform the lens wide open. Of course, you can stop down if you need the depth of focus. It's not possible to use it always wide open. Sometimes I'm kidding to say there should be a question within on camera. Are you sure? Do you really want to stop down? Are you sure? Like Windows, are you sure? Do you really want to do this? We should ask the customer, are you sure to stop down? Just kidding. You can use your lens as like you want, but to to realize best performance in terms of image impression and all these things, use it wide open. So third generation from 1989 with Aspheres is indicated here. We are still in analog times here. Sorry. And here you see the focal length again, and here is the F number. All the lenses are equipped with Asphere. Only these two lenses were not equipped with Asphere at that time. In the second generation, so this I already explained, the perceived performance. This becomes normal, and the next step innovation was done by Asphere Technology here, and by floating element we increased the performance without increasing the size too much. Floating element needs a little bit more size. So, and let us have a look at the third generation. So light flux is done to 10, 0.95. Who need more? I don't know. Who needs more? And compactness is there, but we had to reduce a little. We had to add some space for floating elements. So I said, okay, it's 8 in comparison to that what we have done before. Image performance is best now because, as I explained, there is no need to stop down. And there is no, so this means there is no best aperture, only the wide open is best aperture. The ease of use and the robustness is there still. And we did a lot about robustness in terms of humidity test and so, because we improved our coatings. And the reflection coatings are not only for anti-reflection, these are also coatings to protect the lens and against scratches and protect the lens against humidity and all these things. We did a lot. We still are looking for improving this robustness. So the M classical CSC limitations of I already explained, the advantages I explained too. And the expectations today were the camera should be digital, compatible, zoom lenses should be possible to apply, 35mm format should stay, close focus should be better, autofocus should be implemented, and ease of use should be there. And here, the second challenge or the second crisis for the M-System was the digitalization of the M-System. And this was, when we are told, or it's often told in the internet that we missed the train or we nearly missed the train. It looks like that, but in principle it was very, very hard to find a digital system that fits to the M-System. The reason why, due to the compactness of the system here, you can have a look into the camera. This is an M lens, a 28 2.8, as I think. It's very compact, very close to the sensor here, and the rays or the light is going through the system and with a steep incident angle on the sensor. And at that time, beginning of digitalization, all sensors, it was said the sensor need to have telecentric optics. This means rectangular incident angle to the sensor. And this is not possible to realize with M-System, or if we would follow this concept, we had to stop M-System and had to find a new system that fits to the sensor. And so we had to find a way to overcome this problem. And in principle, here you see the reason why it is. Each pixel has some certain barriers, and if a light falls into the sensor like this, it will be vignetted. So the light will not fall onto the pixel. This is a sensitive area, like here, yes. On axis, no problem, but off axis would be dark, like here. And what did we do? We implemented a micro lens offset. In front of each pixel, we implemented a micro lens that is offset depending on the height, different offsets depending on the height. And with this, we could realize the digital system. This was done in cooperation with Kodak. Kodak helped us a lot because they implemented the microlens system in front of the sensor. And so I would like to say we were the pioneers regarding compact system cameras to make it digital, yes. And we pushed the limits of the technology because we were the first who implemented this sensor technology or this packaging of the sensor to keep the M-System. And we fitted the digitalization to the M-System and not the other way around, yes. So we didn't miss a train, but it was very hard for us to find a solution that fits to your expectations as a customer. So, and today we have a third generation M-mount lenses with Aspheres and floating elements indicated like here. So these are the latest lenses. This is the 90 1.5, the Noctilux 75, and so forth. Yes. And yeah. And let's take an example, the 21 millimeter, the performance of that. Here, the total shift of the system is 0.5 millimeter because it's 21 millimeter, it's very short, and here is implemented the floating element, and floating element improves the performance in close focus. You need to know if you have as wider the aperture, as short, as smaller the f number, it's more sensitive the system is due to changing the distance, the object distance. It can't be optimized for all distances without implementing some compensators, and this is a floating element. And here again, I would like to show you the setup of the 21. Here you see that this first surface, this first lens element is fixed with this barrel, and this barrel is optimized with a high precision turning and milling machine. Here is shown here. Yes. And again, very compact and precise focus mechanism was needed, again, similar to that what I have shown of the Noctilux. Yes. And the second innovation was needed to have special lens hoods, because if we would use a round lens hood, we wouldn't be able to use the rangefinder. So we had to go follow this concept, the point cut lens hood thread. Yes. This is this is an innovation done by Leica, and we filed a patent to that. Yes. Just to explain. So let's have a look at the Noctilux 75. Fastest lens, 75. Maximum effort for optomechanics, of course. Smallest depth of focus. Very high optical performance, and Aspheres and floating element were implemented. Yes. This you can see in our brochures. And again, highest performance, this is for 40 line pairs, nearly to the edge, but not only at infinity, also close focus. I talked about at the beginning about depth of focus tables. This table is based on the 30 micron circle of confusion, allowable circle of confusion. We know that it's much smaller today, but what can you do with this small depth of focus? Yes, you can take pictures you wouldn't be able to do with other systems, like this picture. This is my dog, or the dog of my wife, and this is the mechanical designer of this system. This is one of the very first pictures I took with the 75 millimeter lens, and here you can see how clear and sharp and the three-dimensional impression you can get, even though it's a two-dimensional image. And I would highlight again this is a picture I like really very much, because it's so crisp and sharp and so three-dimensional, and you can realize this with our lenses. This is Leica Look. This is Leica bokeh. This is the precision we put into the design, but not only we put it into the mechanical precision, the optical precision, in the final assembly steps and all these things. Yes. And you can go closer and you see more. This is still the same picture, even though it's a stiff situation. Yes, I know, but I didn't change the JPEG. I don't like to use Lightroom because I use the computer all day. I don't want to do it in my spare time. And so, but it's still crisp and 3D. This is what I want to express. And you go closer and you see more. Yes. Yes. Again. Yes. So. And here is a concept behind each new system we introduce with innovation is very expensive because we have to test all processes and all these things. And that's the reason why we try to implement platform systems so that we use the technology we developed several times. And so the idea was to scale up to 50 millimeter and due to the fact that the entrance pupil shouldn't be bigger than 60 millimeters, so we decided not 0.95 for the 75, but 1.25. And if you divide 75 by 1.25, so the entrance pupil or the first surface diameter tends to be 60 millimeter, and this was a limit. And so we did a platform for this both lens systems. So here the first group is similar with both the 90 and the 75. Yes. And again, I would like to highlight what are you doing when you stop down. When you have 0.95 as the maximum aperture you can use, you have 100% light flux. If you stop down to 1.4, you only use 50% light flux the lens is able to transport. And if you stop down, in this case, down to 5.6, only 3% of the performance of the lens will be used, to make it clear. Huh? So, are you sure? Do you really want to stop down? Or let's just say different. Do I really need this aperture, or should I take a smaller one and use this lens wide open? And there's a German rhyme, die Sonne lacht, blende 8. This means sun is laughing, use f8. This is not a rhyme. I wouldn't say let's use ND filters to use the creativity of this. Enables you the wide open lenses. Yes, never stop down if you do not need the depth of field. Please. So again, let's have a look at the perceived performance. So now that the light flux is 10, yes, again 34, and here you see innovations were needed to improve the performance, and we always try to keep the targets high so that you can have the best tool to get good images. And let's have a look at the expectations today. Nearly many things we could accomplish. So live view compatible zoom lenses can be applied, even though we don't have so many zoom lenses for the M, only one at the moment. Close focus, autofocus and ease of use is not there. And the M camera is the M camera. The M camera teaches you need to be open to use the M camera, and you need to be open to be taught by the M camera. But you are the master of the final system, of the final result. No automatic functions regarding autofocus. This is the compromise you have to take into account. And if you are interested in autofocus systems, I would like to invite you for the next presentation. Next week, we talk about SL, perhaps a little bit about TL and CL. And if there is more time, I could continue with my additional slides. May I?
Yes, I think that would be great. I'm sure everybody's still listening. I do have quite a few questions at the end for you, but if you want to go a little bit further, and absolutely, please do.
So questions now or first continue?
I think you want to show some of the macro stuff you were doing. Is that right?
Yeah,
Yeah,
that's
well,
right.
let's do that, and then we'll do the questions at the end.
Oh, so now this is my private view on the M-System. You shouldn't use it only for that. That's the main target. You can use it. You also can use ND filters. You can then use the Noctilux and the macro adapter, and with M Live View you can take pictures macro. We don't need to talk about performance because, as I explained, wide open lenses are very sensitive regarding changing the object distance. And so in this case here, for example, this is a Noctilux image. The performance is low, but it's a different kind of dreaming images you can take. And one vacation I used only to take these pictures because I was so fascinated by this. And again, this is not movement, these are aberrations, what I are looking at, yes. and this is, yeah, nice pictures. This is a 90 millimeter f2, I think, with a macro adapter. Again, Noctilux, as I remember. Yes, these are the roses of my wife in our garden. Yes, really. And here is a explanation how you can use all the lenses, the magnification without and with the macro adapter. So you can, I wouldn't say this is perfect, but you can try whether this fits to expectation, whether this fits to your target. Dreamy pictures, I would say. Okay, that's all. Thank you very much for your intention.
Right,
Thank you very
fantastic.
much
Round
for
of
your
applause, I
patience.
think, for Peter there. I had a lot of really good comments coming, and everybody's really blown away by the level of detail and just sheer effort that goes into the Leica lenses. I really don't think people understand exactly how much effort goes on behind the scenes. And I know when I visited the Leica factory myself, I'm astonished to see people working those M lens focusing rings. They're working them by hand to get just the right feel as you focus the lens. It's perfect. It's just astonishing. So do you want to unshare your screen or stop share for us, Peter?
Yes.
And then I will ask you some questions. I've got quite a few. We'll see how many we get through. There's a couple here you may not want to answer. We'll see. So, okay, going back to the beginning. I think that one's been answered. Oh, here's a good one to start off with. Mark Chan would like to know, what are you hopeful for the future direction of optical technology? What do you think we might achieve? Higher resolving lenses or 3D dimensionality?
This is a combination of both, I think, yes. Higher resolving and 3D is close by. If you only look at higher resolving, you can stop down, but if you have use it wider open and the resolving power is the same, you have the 3D dimension, the 3D impression in best way, yes.
Okay. Okay, because I know that there's been some work done on computational stuff as well. Is that something that you're starting to bring in with the lens design as well?
In some cases, we use image enhancement by software, yes, but computational imaging, that what is going on the smartphone area, we do not implement today within the M-System, but perhaps we can it depends how this is a processor issue, and a mobile phone has a good processor inside, yes, very high level, and so but the M-System, I think, is more oriented to the natural impression. Lenses can perform best if they are clean, yes.
Okay. Tony would like to know about the limitation on, Hung Nguyen, would like to know what about the limitations of the zero 0.7 meters close focusing. Why are almost all the lenses limited to 0.7?
So the rangefinder system is limited by 0.7. And that's the reason why the lenses were limited. So we have the trial the wide angle trial enables you to go closer, but you can't use the rangefinder system because you can't look so in that direction so close. But today we can think through whether we can change it, yes.
I just learned something. I didn't know that. That's cool.
But first, the M3 was limited by 1 meter. That's the focusing range, and the M7 and all the successors were limited or are limited by 0.7 meters. Yes.
Okay, there we go. That's news. That was news to me, that one. Tony would like to know, and this is one. Well, you can answer this however you like. Is there a reason that lenses wider angle than 50 millimeters are not crafted with Noctilux apertures?
The reason is that the market doesn't ask for that.
Okay.
All right. So mainly focused on 50 millimeter and so forth. Yes, but in principle, there is a wide spot. Yes, it's a wide spot.
So in principle you could, but nobody wants them.
Nah, I wouldn't say nobody wants, but we can't do everything at the same time, and so we have to go step by step.
Okay, yes, this is an interesting one. Terry Forrester would like to know, and I'd like to know too, how far does the image deteriorate when a lens is stopped right down to a small aperture? Because that's diffraction, isn't it? And I just love a comment about that.
Yes, it's diffraction limited, yes.
So at what point would you say diffraction limits the resolution?
8, f8.
8?
Yeah.
Okay.
So if we are, that's funny. So our competitors or some competitors publish MTF curves, geometrical MTF curves, and we publish diffraction MTF curves. So sometimes you see geometrical MTF curves where the performance is 90% and higher, even at 5.6, and this is not possible because diffraction appears there. So you always need to, if you compare MTF curves from different vendors, you need to know, is it diffraction or MTF, or is it geometrical MTF? Okay. So one vendor is delivering both. We only diffraction because this is close to that what you are using at the end.
Okay, all right. Danny Tiong he wants to talk about zoom lenses. He asks, one of the disadvantages of M camera is no zoom lens. We have the Tri-Elmars, which is sort of a zoom lens, but is there ever, what do you think about true zoom lenses for M-System?
The true zoom lens, then it's in principle a mirrorless camera, but not an M camera, because continuous zoom and rangefinder focusing is not possible. So either you take a fixed focal length lens or this Tri-Elmar version, because we can't control the focusing for the continuous zoom.
Of course. Now, I believe that the Tri-Elmar does actually work if you have it between the focal length settings, but you can't focus or frame it easily. So that's a good answer, actually. It's because of the rangefinder. Of course it is. It's the wrong system. Okay. Valeria would love, this is another tricky one. Out of curiosity, Valeria asks, if I may ask, there are a lot of rumors about how much time it takes to cool down the special glass that you need to produce the Noctilux lenses. Are you able to comment on that?
This is a process we don't have under control. This is the vendor of the glass material today. So in principle, if you press a lens lens element pressing, so for pre-production, for example, the shape of the original material you use for polishing the lens element has a certain shape close by that what we will have finally, and then they press and then they cool down, and the cool down process depends on which refractive index and which dispersion index we want to have, and it's days. Sometimes it's days. It takes days to cool it down, because they have to heat it up on a very high level, and then they have to cool it down 1 degree by 1 hour or so. Yeah. But I could read this, but at the moment I don't know it.
All right, that's great. Okay. Has Leica put any thought into increasing shutter speeds in the cameras? It's outside the realm of lenses, really, because the SL, of course.
Good point. Then we can get rid of the ND filter. Yes,
absolutely. If you put the Noctilux on the SL, it's SL2. It's no problem because you can shoot with the electronic shutter. But I think it's limited by the mechanical shutter of the M-System. But that's maybe a question for Stefan Daniels.
Exactly.
Okay.
Thank you very much for that question. Please highlight it.
There's an agenda there, I could tell.
As a lens designer, and as I propose, use it wide open, never stop down. You do not need to depth of focus.
Okay. David Cliff would like to know, each version of a lens seems to be an incremental improvement on previous versions. We hear about design, glass and coatings, but what is the real difference from an optical performance perspective?
So we know to use the glass materials because of our history regarding new glasses we developed at the Lights glass laboratory. And so optical wise, we improve the performance by keeping the size, or we enlarge the aperture. Improved performance means MTF is higher. So, and optical wise, and so for this we use different techniques or innovations like glass materials, assembly line. So as better the lens, as more complicated the production is. And to keep the production on a stable level so that you always get a good lens, we have to improve also the manufacturing processes and the measurement technique behind and all these things, yes. And so these steps, these are small steps in each parameter, but it's a next level than we get with a new design.
Okay. David Cliff goes on to ask a second question. Are the new lenses optimized specifically for digital sensors, or are they fundamentally better implementations of the older lenses, i.e. good for film or digital?
So in front of the sensor, there is a filter packaging. And from the beginning, we try to squeeze the thickness of this packaging because it's only a window, it's only flat surfaces. But even though it's an optical element, we have to implement in our calculations. Yes, and that's the reason why we always try to squeeze the thickness to keep the performance of the analog lenses as they are. But today, when we design a lens, we fit it from the beginning to the digital. So there's a small drawback regarding using it at the analog with analog camera, but the differences are small and hard to detect with analog technique. So.
Okay. That's because film has a certain thickness, but the sensor is essentially flat. Is that's?
I wouldn't say so, but in principle you are right. A certain thickness is also where's the image field, yes, where's the image surface. in
Yeah.
detail.
Yeah.
This
Okay.
this is but we design new lenses to fit best to digital.
Okay.
And,
All right.
and we but from my perspective, there is not a real drawback for analog. You can use them. But there
Okay.
is a drawback if you use different cameras from other vendors, S company or so. They have very thick filter packaging in front of the sensor, and this reduces the performance of the lens.
Yeah. Yeah. I think
Especially,
the wide angle lenses are notoriously bad on other brand sensors, and
that's
they
the reason
fall
why
into the corner.
the incident angle is very steep, and if there is a flat filter in front of that, this introduces astigmatism and all these things. Yes.
Okay.
Aberration.
It's a quick question. This is a good one. How long does it take for a new lens to be designed from start to finish?
Too long.
Roughly.
Roughly 4 years.
A year. Okay.
Right.
Wow.
Yes.
All right.
But
Ken Wang would like, sorry.
in some cases we had some we could realize it within 2 years, even though it was a quite new technology we implemented. But to be honest, we have so many projects at the same time, and so it's lots like the autobahn. If there are many cars on the autobahn, you can't drive fast. So that's the point.
Ken Wang would like to know, is it possible to produce an Apo Noctilux 50mm?
In principle, yes, but the size would be too big.
Okay.
So,
All right.
so we can increase the size, but so look at there is one Noctilux lens. It's named different because another company, but it's big. Or have a look at
I know the one you mean. I know
or
what you mean.
have a look at the Cine lenses. Yeah, Cine lenses have the same better performance, better color correction, but it's 3, 4 times, 5 times bigger than the Noctilux, and so possible is it?
I think one thing people don't realize is that the size and the quality are directly connected, and it's very hard to make a small, high quality lens. That's why next week, when we talk about the CL, well, particularly the CL lenses, there are a lot of innovation in those lenses to keep them small and super high quality. So still a couple more questions to go.
I forgot to highlight M lenses are the fastest lenses with high performance in a compact size. These are the three aspects: very fast, very compact, high performance. And these are the three pillars for the M system. And when we look next week to the SL system, highest performance, yes, but not compact in comparison to M, yes.
True.
And so
okay. This leads sort of into next week's talk a little bit, because John Reed would like to know, talking about zoom lenses, and obviously there are zoom lenses in the SL lens range, how can you have a fixed aperture zoom lens when the focal length changes? So surely the aperture must change, they must be connected somehow so you maintain the same effective aperture.
So that's a good point. Next week, I would like to talk about the primes mainly, yes, not about zooms, but depends on what you want. But there we have a flow with the zoom lenses from the SL. We decided to use floating aperture because this is a natural behavior of the lens system.
Okay.
The natural, and it depends on the entrance pupil. You try to keep the entrance, or we try to keep the entrance pupil the same by changing the focal length, and the entrance pupil is always defined by focal length divided by f number. So, and if you have a longer focal length and the same f number, you need to increase the entrance pupil. The other way around, for the short focal length, you don't use the whole potential of the system if you use it with the same f number like the telezoom. So and we didn't want to compromise in performance, but we compromised in the f number.
Ah, that's why. Okay, that
So
explains a bit. Okay, yeah.
F number and size, and of course we could do an f2.8 with, but then we have to increase the size of the middle range, or to squeeze the size and reduce the performance, or it's always a trade-off. Yes, take this or that.
Yes,
and we didn't want to compromise in performance.
Never do that. All right, here's a really great question. If you could choose one M lens that was made for film cameras, not digital, which one would you choose and why? So this is to use on a digital camera now. Sorry, so a film lens, but to use on a digital sensor now. Which one would you choose and why?
So my preference is a 1.4 50 millimeter. Yes.
Okay.
This is the masterpiece. My masterpiece, I always think, and the size, performance, and f number, best compromise. Yeah.
Okay. Which year was
better lens is the f2, the aposomicron 50. Yes, this is
true.
It's talking like your grandchildren. Which one do you like most? I always. Once I talked with somebody, with David Farkas, and I said to him, "Oh, the 75 1.4, the Zumilux, the older version, is not my preference." And he wrote in the internet, "I don't like it." That's not true. It's not my preference. So please be careful with my answer.
Sure thing. Okay, just looking down the questions there. This is a little bit technical. Eric Breckpot would like to know, is there a way to find the t-stop values of lenses? It would be interesting for comparison purposes. So is an f0.95 optic, does that let more light through than a t1.2 lens?
I think the 0.95 is a little better than T1.2. I think 1.1 or so, yes.
Okay, that's good.
But,
all right.
This discussion about T, this was relevant for the analog film industry, because when they changed the lens, they need to have the same exposure independently from the F number. They need the T number so that they have the same T number. So I understand, but today, T number, who cares?
I've noticed they still have the T number on the Leica Cine lenses, but that's because
because the film industry is still in that thinking.
Yeah. Okay. All right. I think that's all questions. That's everything, I think. I hope I haven't missed anybody's questions. A couple I didn't ask because I think you covered them in the talk. So thank you so much, Peter, for sharing that presentation. Judging by the comments, everybody's sort of sitting there with their eyes wide open going, I had no idea how tricky this stuff was. But I think, we all know from the results that we get, those of us who are using Leica lenses, that it explains a lot about how good the results are, because when you see what goes into them behind the scenes. So next week, as Peter said, we're going to be talking about the SL lenses, particularly the Summicrons. What have we got now? There's the 35, the 50, the 75, the 90. And I've used all those lenses personally. They are absolutely phenomenal. So join us all next week for a second installment of Leica Lens Design. And thank you, Peter Karbe, so much for taking your time to share that information with us today.
Thank you very much for giving me the chance. It's a pleasure for me. Thank you.
Great. It's been really good. So everybody's saying thank you on the comment screen here. So it's been really good. I'm going to shut down in a sec. So if Peter, you want to leave the meeting, I'll say goodbye to everybody, and then I'll email you briefly in a second. Okay.
Thanks,
Peter. I'll talk to you next week.
Bye. Okay. Next week.
So thanks, everybody. We'll be back same time next week. So do join us then. I'll just leave the web address on the screen for those people who want to join the mailing list or want to sign up for or look at the YouTube channel. So that's that one there. And I'll leave that on the screen. And goodbye from Nick Rains, Leica Academy Australia, and we'll see you again next week. Bye for now.